Good afternoon, everyone. I will give a sharing topic about the spatial-temporal indoor crowd interpolation and the prediction with graph neural networks. And this is the outline of today's sharing. So firstly, I will introduce the importance of the crowd analysis, then our proposed methodology about the GNN, and I will introduce the case study and results conducted in our Hong Kong UST, and then the conclusion and the future work. So let's directly go to the crowd analysis part. So the background is that the crowd analysis is crucial for the smart city management, such as space management, safety, and well-being. And you can observe from the figures below here, there are some crowd surge in the South Korea and at other places in the world. So the crowd management is crucial in the city management. And the right-hand side is a figure about the higher density of the crowd indoors can trigger higher value of the CO2. So this shows the relationship between the CO2 and the crowd. So and after that, the indoor sensing about the crowd actually have some limitations because of the privacy issues. That means the direct measurement, like the CCTV monitoring, are limited. So in our study, the indirect detection is also utilized, like the Wi-Fi and the Bluetooth. And the existing studies about crowd analysis, there can be divided into two different approaches. The first one is the data-driven studies, which utilize the IoT sensing and the CCTV, etc., to the crowd detection and the prediction. But this is limited by the spatial resolution. So you can observe there are two studies listed above. The first one utilizes the temporal issues of the crowd prediction and expanding the time gap in the prediction result. And the right-hand side is the local side of the spatial-temporal crowd density prediction, but is limited also by the scale. And in the lower part shows the crowd flow simulation, which is another approach based on the simulation. This is relying on the crowd simulation and also the different logics about the crowd density. So you can observe this is an example we have conducted in one shopping mall, and we have modeled different logics about the crowd flow in, flow out, etc. And also some studies also utilize the beam supported emergency simulation based on the crowd density analysis. And let me directly go to the limitations about the aforementioned studies. Because we are utilizing the GNN in the spatial-temporal analysis in the current studies, the limitations about the recent studies we have reviewed. The first one is the reliance on the predefined graph topology. Because you can observe here, this is one difference between the static graph and the dynamic graph. We can also call it the time-evolving graph. And in the GNN model, the message passing is really important. And if we miss the sensing data in the B here, the computational graph we can observe here from that. Then the message passing mechanism will fail in the following sessions. So this is really important for the spatial-temporal graph here. And the right-hand side is one study that conducted the study about the indoor air quality interpolation based on the outdoor air quality station. But it's actually limited utilizing the simple GCM model. So we ignore the temporal dependency like the traditional STM, GRU, etc. This leads to the spatial sparsity and the temporal sparsity issues are actually underexplored in the previous task. And when we talk about the GNN for the time series, you can observe there are major 4 different tasks that to address the different problem in the spatial temporal data. And the actual difference, there are 2 different tasks that address the data quality issues, but there are the prediction studies and the imputation or the anomaly detection are actually examined in the separate study. So this is one gap in this study, in the previous study. Yeah. So our research goal, firstly, is to develop one hybrid dynamic GNN model to improve the resilience of the spatial-temporal crowd density prediction. And we address the data quality challenges, such as the missing node and the incomplete graph topology in the spatial-temporal graph. And then we formulate the two different tasks in one integrated framework to combine the two different tasks in the robust crowd analysis. And this is the general workflow of the proposed framework. You can see the data sources are from the IoT sensor portal and the beam model, which is with both from our case study and the data collection. The sensing data is actually the 6 minutes resolution, and the beam model for the spatial topology is also proposed. And then we formulate the spatial-temporal graph construction, which is abbreviated as the G0. We include the node represented for the sensors and the edges represented for the distance. And this is the graph F is actually based on the spatial graph topology. And after that, we do the graph subsampling based on the masking node and simulate the sparsity issues and also the incompleteness in the data missing problems. Then the dynamic graph reconstruction using the cosine similarity and also the graph attention network is also adopted. Then we do the model prediction and output via our proposed model here. And to tackle the different missing problems, we can observe the different situations here. There are some scenarios that not formulating the different subgraphs, and there are some also formulating different subgraphs, even the single nodes here. So this is the main concern in our study, because this has a higher difficulty in the interpolation and also the reconstruction of the graph topology. So let's go through the proposed model, which is called the spatial-temporal attention-based interpolation and the prediction model, prediction graph convolutional gate recurrent unit, which can be abbreviated as STAIP-GCGRU. And the key component here is firstly the GAT module, which assign the dynamic weight to the different to their different neighbors. And based on that, and after that, we can utilize the GCGRU module to combine the GCM and also the gated recurrent unit to do the temporal embedding via the gated mechanism. And we can observe the GCGRU module as a simple structure like this one. We combine the graph convolution in the GRU module here. And finally is the MLP, which projects the hidden states to the different dimensions. And the key innovation here is we adapted a graph topology dynamic utilizing the similarity and the attention, enabling different prediction and interpolation tasks here. So our data set, we utilize the Huang University campus. We selected 9 high traffic areas, including library, atrium, canteens, academic building, etc. And then the temporal dimension, we choose 2 months data sets, including more than 10,000 timestamps. And there are different settings, and we have chosen the baseline utilizing a different GM model. And the important thing here is a loss function. We also utilize integrated joint spatial temporal learning because we treat the prediction and the interpolation task as a as the 2 different tasks. And for simplicity, we choose the alpha equal to 0.5 for simplicity. And these are the curve fitting capability and the quantitative analysis results. So you can observe here in the prediction results, our proposed model performed similarly with the baselines. And for the interpolation results, our model performed better than the different baseline models, and had compared with different models, even had many capabilities to capture the different peaks. And to conclude our study, our model integrates interpolation and the prediction tasks via the dynamic graph updating mechanism, and which can outperform the different baseline by handling the sparsity data and also the dynamic dependencies. And for the future work, we will incorporate with more crowd sensing data with increased availability of the data set. We can observe here, although we don't include in this conference, but we have conducted more recent work related to the heat mapping based on the interpolation results, compared with the IDW-based approaches, etc. And these are the reference for my work. Yeah, thank you.